In this work, we present PolyFly, a polytopic optimal planning method for collision-free, cable-suspended aerial payload transportation systems. Aerial transportation robots are becoming a reliable technology in providing emergency services during natural disasters. For example, they can be used to transport critical medical supplies during indoor rescue operations after an earthquake or in outdoor missions during forest fires. A key requirement to making these systems efficient is to develop methods that allow them to quickly navigate cluttered scenes and fly in close proximity to obstacles. To enable such navigation in crowded scenarios, our planning method employs a non-conservative spatial representation. We do this by modeling the robot using three distinct polytopes, one for the quadrotor, one for the cable, and one for the payload. The environment is equivalently represented using one polytope per object. This non-conservative representation allows our method to accurately compute the minimum signed distance to each obstacle, denoted in this figure by h. Unlike most other methods, as shown by the blue sphere here, we use an orientation-aware polytope to represent the quadrotor, which allows our planning algorithm to generate collision-free trajectories in tight environments. We impose the polytope-to-polytope distance constraint using a signed distance constraint. On the left-hand side, you can see the minimum distance formulation for two polytopes Mi and Nj. Unfortunately, this primal constraint is discontinuous and non-differentiable, which makes it hard to integrate into optimization problems. By applying duality theory, we can formulate an equivalent constraint that is smooth and differentiable. We formulate our optimization problem using a model predictive control approach. Specifically, we minimize the cost function L, subject to system dynamics F, initial and final constraints, and the polytopic collision constraints described earlier. We define the cost function as the sum of four terms: a term that minimizes time, a term that regularizes the input, a term that penalizes deviations from the initial guess, and finally, a term that discourages large changes in subsequent time step durations. We evaluated our method in 8 different test environments and produced faster trajectories than the baseline in each test case. We believe this boost in performance of our method stems from our non-conservative modeling choices that enable flight close to obstacles and the integration of smooth, differentiable polytopic constraints that allows the solver to converge to solutions even in difficult environments. We recreated a subset of these environments in the real world and validated that these trajectories can be tracked by a real quadrotor carrying a suspended payload. The generated trajectories are tracked by a nonlinear model predictive controller running onboard the drone at 200 Hz. The NMPC sends thrust and body rate commands to a low-level PX4 controller. The state of the system is measured using Vicon and upsampled using Kalman filters running onboard the robot. We were able to successfully deploy our trajectories in these tight environments, and as you can observe, the robot repeatedly flies very close to obstacles. This highlights the practical reliability of our method and demonstrates that the generated trajectories are dynamically feasible.